Hi everyone. So in this video, we're going to discuss flux. So suppose you have a velocity field or some kind of fluid field, and you want to measure the flow in the direction of the normal of the curve. So we're going to talk about something called the outward flux. So this is going to be defined as a line integral. So pretty much we want to measure how much of this fluid or how much of this quantity is flowing into the region versus out of the region. So the region here we're defining is bounded by the closed curve C. Then we have a orientation of the curve. We're going counterclockwise, as you can see here from the picture. And the way we're going to do that is that we're going to take dot product of the vector field F with the outward normal, the unit normal of the curve. So be our line integral along the curve C. So we're going to put a closed circle on the integral to specify it's a closed curve, and that's the orientation counterclockwise of F dotted with the unit normal ds. That is our definition of outward flux. And when evaluating this is easier to work with as the integral along the curve C, the closed curve C, put an orientation counterclockwise of m dy minus n dx. So that's the quicker way to evaluate flux rather computing it this way. So leaving out the illustration how we got the formula, let's go ahead and take a look at an example. For this problem, we want to find the flux of the field. This is our field in 2D. Across the following curve, the curve is r of t, which is equal to cosine t for the ith component and 9 sine of t from t goes from 0 to 2 pi. So that's a closed curve. Now, if you remember, this is an ellipse. So we're looking at the outward flux across this curve, which is an ellipse for this particular vector field. So if you were to draw it, it will look something like this. So that's the curve we're looking at. This is the path. So we're starting right here. This is our direction, increasing t value. So this is, well, I guess we can just label that. That's the first point when t is equal to 0. But along the x direction, this is actually 1. And this point right here is actually 9. So that's the ellipse. And we have the vector field, of course. So to calculate flux, we're going to be using the outward flux. So we know that the outward flux is defined as the line integral around this closed curve C F dotted with the unit normal ds. And we know that this simplifies to the line integral along the curve C of m dy minus n dx. So we need to parameterize these in terms of the curve. So we already have what the curve is. So the curve C is parameterized by this equation right here, and t ranges from 0 to 2 pi. So we need to express f as f of r of t. So we're going to evaluate f at r of t. So the first thing you want to do is find f of r of t. So plugging in each component. So we know this is the x component. This is our y component. So let's substitute them into our field. So the first component is negative x. So that'll be negative cosine of t. The second component is y. So that would be 9 sine of t. So that's our f of r of t. And here you pick out your functions. So this will be your m, and this is your n. So use the integral. Now we also need another thing, our derivative. So we need to find r prime of t. So we take the derivative of r of t right here, respect to t component wise. So this will give you negative sine of t. And for the second component, we'll have 9 cosine of t. So those are the derivative. And here again, you pick your components. This will be dx dt. So I'm just going to write dx, and this will be dy. And now we're ready to use the formula. So here, m is going to be substituted right here. dy, we're going to substitute right here. N is this, and dx is that. So after making the substitution, we know that the outward flux of this vector field, so our outward flux, we're going to integrate from 0 to 2 pi, because those are the bound on t, as you can see it in the problem. M, well, m is negative cosine of t times dy, that's 9 cosine of t, and then minus n we have is 9 sine of t times dx, that's negative, so this will be a plus sine of t, and we're integrating respect to t. And then you can separate this into two separate integrals and proceed. So we have the integral from 0 to 2 pi of negative 9. Let's put that outside. Cosine square of t dt plus 9, the integral from 0 to 2 pi of sine square of t dt. And then we use our trig identity to evaluate the integral. All right, so I'm going to replace each of these with our identities. So we have negative 9, the integral from 0 to 2 pi. Cosine square of t, we're replacing that with 1/2, 1 plus cosine of 2t dt. Plus, we have 9, the integral from 0 to 2 pi. Sine squared t, we're replacing it with 1/2, 1 minus cosine of 2t dt. So that is our identities to replace. Now we integrate each piece. So we have negative 9 over 2. I pull the 2 out. The integral of 1 respect to t, that's just going to be t plus the integral of now cosine of 2t. Using a quick substitution, that's going to be sine of 2t over 2. We're going to evaluate this from 0 to 2 pi. Similarly, for the second integral, we pull the 9/2 out. We integrate 1 respect to t, that's t, minus we integrate cosine, so that's going to give us sine of 2t over 2. And again, we evaluate this from 0 to 2 pi. And then by using the fundamental theorem of calculus, we evaluate them. So we have negative 9 over 2. Replace t with 2 pi, the upper limit of integration. We get 2 pi plus sine of 4 pi, that's going to be 0. So we'll get 0. And then when you plug in the lower limit, you're going to get 0 for each piece. So they're both 0. For the second piece, we have 9 over 2. I replace t with 2 pi. That's the upper limit of integration. Minus, as you plug in 2 pi, you're going to get sine of 4 pi. That's going to be 0. And for lower limit for each component, you'll get 0. All right, so everything simplifies to negative 9 over 2 times 2 pi, and then plus 9 over 2 times 2 pi, which will simplify to 0. All right, so the outward flux of this particular curve, of this field across this curve, happens to be 0. All right, I hope this idea makes sense. Take care, everyone.